So, Tom, I'm going to start when my watch says 2 o'clock, which is a few seconds from now. Are you ready?
Yeah, I'm ready. Yeah,
Ready,
thanks.
ready? Okay.
Oh, no, I
Uh,
should share my screen though. Right,
yeah,
that's what I.
yeah, yeah. When you're ready.
Mm, Share screen.
Okay. It's a little small, but yeah, you can get that. Okay, that looks good.
Is
Okay,
that good?
so that looks good. So, Tom, I'll start. I'll start recording now and introduce you if you're ready.
Yeah, I'm
Okay.
I'm I'm ready. Thanks.
Uh, Okay, so I'd like to welcome everybody to the spring 2024 semester of the Western Hemisphere Colloquium in Geometry and Physics. And we're going to start things off with Tom Bridgeland today. Remind you the format is 60 minutes, roughly 60-minute talk, 15 minutes for Q&A. Although if you have questions just feel free to unmute yourself and ask questions in the middle. So it's my pleasure to welcome and introduce Tom. He will talk on geometry from Donaldson-Thomas invariants.
Okay, thank you very much. Thanks, Sheldon. Thanks for giving me this chance. It's a nice big audience. I'm very grateful for that. I saw some of the names. So some people are pretty expert in this already and have heard me talk. Of course, the usual. I apologize to those who've heard a lot of this before, but there's certainly plenty of people who I think maybe this will be relatively new to. So it's kind of a report on a big program that I've been working on for a long time now. And the basic aim is to somehow use Donaldson-Thomas invariants to define some kind of geometric structure. One could compare that with the way we use Gromov-Witten invariants, genus 0 Gromov-Witten invariants to define Frobenius structures. So maybe you have that sort of analogy in your mind. Right, and let me just okay, so here's the plan of the talk, but maybe I just go straight to the introduction and we can come back to that in a minute. So I want to just try and put it in a slightly broader context. I did my PhD a long time ago on derived categories of coherent sheaves, and shortly after that, it became clear that there were some pretty interesting relationships between derived categories and string theory. So it seems that string theory knows a lot about the derived category. And I guess these days we understand, thanks to Kontsevich, that the derived category is the category of topological D-branes in string theory, in the B model. My point of view on all this, I mean, I don't want to pretend that I really understand string theory at all. What I'm interested in really is the derived category, the structure of that thing. And it seems that sort of learning some of the language of string theorists helps you understand this purely mathematical problem. And hopefully there's some kind of interesting things in the other direction as well. I mean, some of the structures that have come out of this are now used by string theorists, the people who work on string theory that I speak to. I guess they're in a very mathematical corner of the string theory landscape. Okay, anyway, there's this wonderful interaction between these two subjects. Just to give a few examples. So I guess fairly early on, certainly when I was first doing my PhD, one of the things we were interested in were equivalences of derived categories, right? Different varieties which had the same derived category. So in fact, I wrote my thesis about this. It was about elliptic surfaces. And certainly I had never thought about string theory at that point, but I guess these days we would consider what I was doing as some example of T-duality, in that I was replacing some torus fibration by some dual torus fibration. And mathematically, the way to describe the relationship between these two spaces is via an equivalence of derived categories. So that was, that's an example of where there's some kind of overlap between these things. And later on, there was this idea of pi stability for D-branes. Mike Douglas introduced this notion. And nowadays, we kind of understand that that corresponds to a notion of stability in derived categories. And this is really nice. There's some kind of very close relationship between these two worlds. And I guess once we have a stability condition on the derived category, we can define DT invariants, and those correspond in physics to something called BPS invariants. Yeah, so I'll come back to this, what's being crossed out here. So again, from a mathematical point of view, one of the constraints I like to work with is I want to just consider natural constructions, whatever that means. So in general, what it means to me is that everything I should work with should be sort of manifestly covariant under equivalences between derived categories. So, of course, if you're a string theorist or something, you just think I've gone mad at this point. But this is the way pure mathematicians work. We like to work with natural structures, and sometimes that is a pain, but sometimes it really makes things simpler because there's only so many constructions you can do. You can't just throw the kitchen sink at it. You have to work in a kind of natural manner. And so this whole project comes about a bit like that, because we're very happy with these DT invariants. If we have, they're manifestly covariant in this way. If I have a stability condition on a derived category, I can compute the DT invariants. If I have an equivalence between two derived categories, then I can transport the stability condition from one to the other. And then if I compute the DT invariants on this side, I'll get the same answer. So it's kind of a triviality, but that's just because we've set up the definitions in an appropriate way. So from this point of view, this business about rank 1 DT invariance or Gromov-Witten invariance doesn't fit into this framework, because it really involves choosing an X. And well, in particular, it's this rank 1 that's bad. You see, I could have an equivalence between two varieties. And in general, well, we often do have equivalences like this. They very rarely take rank 1 things on one side to rank 1 things on the other side. So this is, and of course, string theorists would understand this as well. I mean, this is something you do in a large volume, in a neighborhood of a large volume limit point. It doesn't make sense kind of all over the space. And yeah, so this tends to mean that we end up linking up with non-perturbative aspects of topological strings. It's no good, things which are just expansions about some limit point don't fit very well with this kind of natural business here. So yeah, so that's just one point of view on this. So yeah, that's why I've crossed that out. And what we're going to see in this talk is that in certain very special cases, we can get something like the partition function using a natural construction just coming from the DT invariance. And what we get is not the genus expansion of the partition function, but actually an analytic object, which is an appropriately global thing, which if you expand it near large volume will give you this answer. But so I just find it interesting the way this kind of, imposing this naturality forces you to consider sort of non-perturbative aspects. Okay, so that's kind of the end of the introduction. I'm now going to go straight into, so if there's any questions on that, I'm happy to take them. But I'm just going to go straight into the simplest calculation along the lines that I'm suggesting. Okay, so this is a bit of complex analysis, which you could, in theory, give to an undergraduate. So it's sort of fun. So, okay, so I'm going to fix a non-zero complex number. So here it is, Z. And then I'm going to consider this set here. So it's C star minus the ray in the direction I times Z. So there's, and I do have two of these. I've drawn U plus, but U minus would be the opposite thing with the slit up here. Okay. And then what I want to do is I want to look for holomorphic functions to C star satisfying some conditions. Okay, and so let's take these one at once. The first off is that as I go to the origin in this region, the function should go to 1. the next one is that as I go out to infinity, the growth should be bounded. There should be some constant k, so that the function grows at that speed. Okay, and then the interesting thing is what happens on there's some gluing relation going on here. So if I take the intersection of this guy and its opposite, notice that will be disconnected. It will have this kind of right-hand portion and it will have a left-hand portion. And then, so there are these two relations on those two different overlaps. Okay, so of course this looks very arbitrary at the minute, but we're going to come back and sort of set this in a framework which I hope makes some sense. I'm going to explain why this is a sensible problem, in other words. Okay, so we look at that, and we wonder whether there's a solution. So it's a fun exercise that this problem has a unique solution, and the solution is this. So it's basically the gamma function. And so where do you get this from? So this is, you see, this property here is about epsilon going to 0. In this, that means that the argument of this function is going to infinity. So this is going to come about from the Stirling expansion for the gamma function. Okay, so if you remember the Stirling expansion for the gamma function, it says that the gamma function has some, initial terms. I don't know, w log w and half log 2 pi and so on, and then it's a nice series. And so I've absorbed those terms into here. That's what this is, just exponentiating the initial terms in the Stirling expansion, which is why this is true. And then these overlapping relations are the Euler relation for the gamma function. If you look at this, it's saying that gamma of it's some sort of product of gamma of w and gamma of minus w is equal to this. So that's nearly the same as gamma of w, gamma of minus w is pi over sine pi w, or whatever that relation says. Okay, so that's where that comes from. And then this relation is just saying that the gamma function just has a simple, well, it's meromorphic at the origin, essentially, is all you need for that. So that's this kind of unique solution to this problem. We okay with that? So now I do something totally unmotivated, and this title is a bit over the top, but I had to put it somewhere. So I'm just going to massage this function a little bit, okay? And at the minute, this is rather unmotivated. I differentiate it with respect to epsilon, and I basically integrate it with respect to z, okay? So I can similarly understand what that is. So it's some similar function. Now, depending, instead of the gamma function, we've got the Barnes G function. But still, it's an analytic function. And now it has asymptotic expansions. This is very similar to the Stirling expansion, and it's still got the Bernoulli numbers. Indeed, I mean, you can get this from the Stirling expansion by just differentiating and integrating. Okay, so this is sort of more or less the same information. And then, so that's the end of this example. We got from some relatively simple Riemann-Hilbert problem to this relatively complicated series expansion. And what you want to notice is somehow the problem that I started with, I claim, came from the DT theory of an extremely simple CY3 category, namely the Fukaya category. I mean, this is a kind of crazy thing to say. I mean, the category, I'll explain the category in a minute. A more basic way of saying it is it's essentially the category of the quiver with one vertex turned into a CY3. It's a category that's generated by a single spherical object, which is, of course, what you would see here. I mean, this manifold has a single sphere in it, the S3, and so the Fukaya category, I'm claiming is very simple. It's just generated by this sphere. And then this sum is somehow the genus expansion of the B model partition function for X, I believe. So I think this is something like the C equals 1 string or something. I mean, I fished this out of some old paper of Ghoshal and Vafa. But anyway, I'll leave you to agree or not with that. There's other examples where it's much clearer. Because this is B model, I'm a bit all at sea. If it was the A model, I would know this was the Gromf-Witten generating function, and then I would be happy. But the B model partition function, I don't really have any independent way of computing. But okay, so this is some baby example where I got from the DT theory to some partition function, and I didn't just go to the just to this generating series. I actually got an analytic function. Okay, so that's somehow some small version of this story. Okay. So now we can have a look at the plan of the talk. So that was the introduction done. I want to now sort of try and set this problem in its natural context. So I'm going to talk a little bit about stability conditions and DT invariance. And then we're working towards formulating a more general version, a whole class of problems that look like the one I just described. And to really motivate that, I need to talk a little bit quickly about Stokes data. And then I'm hoping, well, I definitely want to get to this thing where I somehow talk a little bit about what comes out of this program. Okay, so I'm going to go relatively quickly through this. So, because in a way, it's not, either you know this stuff or you don't. I mean, you're not about to learn all about derived categories and stability conditions, but it's good to at least know the contours of what's going on here. And I will draw a cartoon picture which might help. So in the mathematical framework of this, the kind of framework we work with in this subject, we take triangulated categories. So that's something like the derived category of coherent sheaves, for example, or there are examples constructed using quivers. And very important for us is this CY3 property, which is this symmetry. And that, in the geometric context, that would be Serre duality on a Calabi-Yau threefold. So anyway, we look at categories with this property. And now I'm just going to introduce some kind of notation, essentially. So I have to choose something which you can call a charge lattice. So there's this thing called the Grothendieck group of the category. It's an abelian group, but in general, it will be absolutely huge, usually infinite rank. So it's good to fix some kind of quotient. So in the example of the derived category of coherent sheaves, you could say, you could take this to be the Chern character and this to be cohomology of your variety, something like this. And in general, I mean, almost always, if you take the derived category of coherent sheaves on a variety, say a compact variety, this group will be infinite rank. So that's why we like to pass down to here. And then we also want to take some skew form on this thing, which computes what we call the Euler form. It computes the alternating sums of the X groups, or the HOMs in this triangulated category. So I think if you're a physicist, you're probably pretty familiar with this kind of data, a charge lattice and a skew symmetric form. And then I want to introduce some Poisson algebraic torus, which is going to be this thing. So it's just the torus whose character lattice is gamma. And so here are the functions on it. And I define the Poisson bracket just using this intersection form. Okay, so we have some nice, Poisson torus. Okay. And often I'm going to accidentally assume that this form is non-degenerate. Notice that I haven't assumed that this map is surjective. You often might imagine it's surjective, but it doesn't need to be. So I can always fix this to be non-degenerate by just embedding this in a kind of doubled version. I can just replace gamma with gamma plus its dual and put the non-degenerate form there. So often I'm going to assume that this thing is non-degenerate. Okay, a quick lightning tour of stability conditions. So just the basic facts of what you need to know here. So in this context, when you have a triangulated category, there is a notion of a stability condition. And it consists of two pieces of data. Actually, this second one is the easiest one. It's just a map from this charge lattice to the complex numbers. We call that the central charge. And then there is also this subcategory of semi-stable objects. And a semi-stable object has a phase. So you have a subcategory for each real number, and that's the semi-stable objects of phase phi. And then there is some list of 5 axioms that these things have to satisfy. And then we consider the set of all possible stability conditions on our fixed category D. And then this rather remarkable fact is that this thing is a complex manifold. And actually, the reason for that is that, and this was kind of Mike Douglas's key idea really, is that if you deform the central charge, there's a unique way of redefining the semi-stable objects so that you still get a stability condition. So, the mathematical way of saying that is if I consider the set of all stability conditions and I consider the forgetful map, which just remembers the central charge, then this map is actually a local homeomorphism. And it's kind of a bit of a miraculous thing. And so then since this is a local homeomorphism, I can just use this as a chart, and this makes it a complex manifold. And because everything here was perfectly natural, we get an action of this group of, so this is the group of triangulated orthoequivalences. But this is a very natural group that, I think, if I gave you some computations of this, as string theorists would recognize them. These are, I don't know, people sometimes call them quantum symmetries or something, but anyway, it's a very natural group. And then we're going to be interested in DT invariance. And of course, this is some vast story, which I'm just going to completely skip. And so I'm just going to assume that at each point of my space of stability conditions, there are some DT invariants, which in some sense count semi-stable objects of class or charge gamma. Okay, so for each class in my charge lattice, there is some number which is counting the stable objects or semi-stable objects. And, we don't really have, in full generality, we don't have this. I guess, this may improve in years to come. I mean, there are many examples when we do have this, of course. For example, in the geometric setting, when we have coherent sheaves on Calabi-Yau threefolds. So what I should say is that also we don't, although we always have this space of stability conditions, it could easily be empty. So I really should have said this is a complex manifold, assuming it's non-empty. Okay, and it's actually a notoriously difficult problem to construct any examples of these things on compact Calabi-Yau threefolds. So there are tons of places where it's easy to construct them. For example, a local Calabi-Yau manifold, or there are categories that you build out of quivers with potential, and then it's just really easy to construct them, and then it's definitely a complex manifold. But it was only recently that Chunyi Li was able to prove that on the quintic threefold, there are stability conditions. And so as soon as you know there's one, this thing is a complex manifold. So constructing examples is hard. And then once you have this manifold, constructing DT invariance is also kind of a hard thing to do. You need further properties of the stability conditions. You need to be able to construct moduli stacks. These need to have nice properties and so on and so on. But for example, on the quintic, we would know that these, at least in some region in stability space, we would know that these invariants exist. But and for quivers or something like that, we would definitely know that they exist. But in general, there's work to be done here to construct these things. Yeah.
So the omegas in general are not integers, you're saying they're rational?
Yeah, that's a good question. They're on walls. You might argue they're not even defined on walls. I don't know. I mean, if you're a generic stability condition for gamma, then it's conjectured that these should be integers. And I think in many cases that would be known, but I don't think it is known mathematically for example, the quintic threefold for a compact Calabi-Yau. Someone else might be able to correct me on that, but I'm not sure that is known. Although certainly,
so let's see. Are you defining the omegas from the DTs? By inverting that formula? How are you defining the omegas then?
Yeah, correct. That's what I'm doing. Yeah. Yeah. Okay, but I'm just going to assume this package. there are plenty of places we know this works, and there are some extremely simple examples where I don't know what to do, how to do the rest of what I'm talking about. So this is really not the logjam in my talk. But I just want to say that I shouldn't just write this down as if it's trivial. Okay, and then so this is the picture you should have in mind. If you fix a stability condition, there is some kind of associated ray diagram. It's a very simple thing. You just take the rays through the central charges of all the semi-stable objects. Okay, so in general, these rays, there's only countably many of these rays because they're kind of they're given by Chern characters in a lattice, but they could be dense in all sorts of regions. And in general, usually they are dense, but in some simple examples, they're not. Here, for example, we're talking about the derived category of coherent sheaves on the conifold, on the resolved conifold. So that's a space with a single P1 in it, which I'm calling C, and the semi-stable objects are just all the line bundles on that P1 and also the D0 branes, the points. Okay, so your ray diagram looks like this. This is for some particular stability condition. Of course, these points are the central charges of those branes, and as I move in stability space, these points will move. So these rays will all move around. Okay, and then this is where it gets a little bit more tricky. So to each of these rays, I want to associate some kind of Poisson automorphism of that torus that I introduced before. Remember, this is the torus with character lattice gamma. And the way I do that, there's two ways of writing this, but I'm telling you what this automorphism does, how it acts by pullback on characters. So if I pull back a character by this automorphism, I get a sum of characters given by one of these formulas, whichever you prefer. So this is a Hamiltonian vector field, and I take its exponential. Take its time one flow, in other words. And I mean, you should notice that these are infinite sums, infinite products. It's not clear that this makes sense. I've also sweeping some signs under the rug here, but let's not worry about those. It's what's called a quadratic refinement. Okay, but it's really the infinities here that are the problem. And so you definitely need to do some work at this point. And so sometimes you can get away with considering formal series. Okay, so instead of these Laurent polynomials, automorphisms of the ring of Laurent polynomials, you could consider automorphisms of a formal power series ring. That kind of works for the wall crossing formula. It works if you're considering rays that all live in a kind of half plane or a convex sector. But for what we're wanting to do later, that's actually not good enough. So we really need to make some assumption here. And this is the assumption we have to make, that the DT invariants don't grow too fast there's not too many of them. So that this sum converges. If you have this assumption, then this sort of formula makes sense. You can use it to define not really an automorphism, but a well-defined map, at least, on an analytic open subset of the torus. So that's what we have to do. But this assumption, physicists tell us that this assumption will not hold on a compact Calabi-Yau threefold. If I take the derived category of coherent sheaves on a compact Calabi-Yau. So that's a big problem. I basically don't know what to do about that. But being an optimistic mathematician, we can understand many interesting things in other contexts, like local Calabi-Yaus, things like that. And I can't really believe that nothing is true in the compact case. Clearly, you need some new idea, or something new has to be brought to the table. But I don't know. It feels like something should happen there too. But for now, I definitely have to assume this. So here's the kind of picture to have in mind of stability space. So it's important actually that I quotient by this big discrete group, automorphisms of the derived category. Typically, stability space itself, you tend to expect to be simply connected and possibly contractible. Really, it's the quotient that's kind of the interesting thing, or that sort of matches with spaces of vacua and string theory or whatever. So here's the picture. It's got some topology. It's got some directions you can go off in, which correspond to large volume limit points. So you know, in some direction, you might be talking about basically Giesecke stability on some variety x1. In some other asymptotic regime, you might be talking about Giesecke stability on some other variety x2. These two have got the same derived category. And so you know, there may be many different varieties with the same derived category of coherent sheaves. And so each of those, you can sort of see their large volume. There may be sort of holes, missing points, which kind of are conifolds, and you know, where the mass of some brane has gone to zero. There may be points with special symmetries like orbifolds or Landau-Ginzburg points. And then there is this very complicated collection of walls where stability, which objects are stable, is changing. And again, those in general are dense, those walls. But if you fix some churned character and you're only interested in objects of that charge, then locally these walls will be finite. And you'll have a bunch of chambers where the stability is constant for objects of that class. And then at each point, you have this ray diagram sitting in the complex numbers. And as you move around, these rays move around and collide. So that's the kind of picture we have. Okay. So now I want to, so this, we've talked about this ray diagram and how each ray in it has associated a kind of group element, which is this, an automorphism of a torus. And so I want to, and we're going to end up considering a Riemann-Hilbert problem where the jumps are controlled by these rays, where, you know, we're going to have some function which is locally holomorphic in each of these sectors, but which jumps as you cross a ray. And I just want to motivate why you would think about such a thing. Where does that come from? So this is this little detour. I'm going to do this relatively quickly, but it's a piece of maths that is nice and it's good to know. So this for now is just an analogy, okay? So basically, instead of the group of automorphisms of that torus, I'm going to think about a more familiar group, which is GLNC. Okay, so just n by n invertible matrices. And I'm going to take a trivial G bundle on P1 and write a meromorphic connection on it. But in more concrete terms, I'm just writing a matrix differential equation. Okay, so Y is a function from C star to the matrices, and I write down this differential equation for some fixed matrices, constant matrices U and V. Okay, and I want to make some assumptions here. I want U to be diagonal with distinct eigenvalues. And actually, I want V to have zeros on the diagonal, just for simplicity. Okay, so what you notice about this connection is that it has a double pole at the origin. And that's a sign that this is an irregular singularity, and there is some story about Stokes data that we have to consider. So I'm just going to quickly explain that. So first, I'm going to define a bunch. So this is what you do. You define a bunch of rays, and the rays are these ones. So they're spanned by the differences in the eigenvalues. What you should think of that is it's the pairing between the roots of the roots of GLN, of the Lie algebra GLN, with this element of the Cartan, right? So the roots live in the dual of the Cartan. So I compare this element with the roots and I just get Ui minus Uj. So later we're going to want to think about the analog of U as being the central charge and the analog of the roots being the characters of that torus. And then this would become Z of gamma, and these would be the same rays we considered before. But for now, this is just these rays. And so I've drawn the rays. These are the red rays. These are the Stokes rays. And then the theorem you need to know is that if I take any half plane, so centered on some non-Stokes ray, so if I take a different ray that's not one of these red guys, and I take the half plane centered on it, then there's a unique solution in this half plane with this asymptotic behavior. So that's the theorem I'm going to throw at you. And if you wonder where this came from, if you look back at that equation, if you set v equals 0, then you can easily see the solution is e to the minus u over epsilon. So that's where really that's come from. So the solution should look like e to the minus u over epsilon plus times some kind of corrections. Okay, so in each half plane that's not centered on a Stokes ray, there's a unique solution. There's a question maybe, is there?
Yeah, are we allowed to ask questions in the middle?
Absolutely.
Yeah, just for you, Daniel, yeah.
Okay. Yeah, sorry, and I don't have my camera set up, so it's a little anonymous. But anyway, at this point, have you used the diagonalizability of U? Have you used those assumptions on U and V, or is this something that holds more generally?
That's a good question. I haven't used V, but I wouldn't. I think I probably have used the diagonalizability of U and the distinct eigenvalues. I mean, something will be true in general, of course, but yeah, I've really used that, I think.
Okay, thank you.
Okay, and then what are the Stokes factors? So I claim that for each ray, there's an associated element of the group G, which is GLN. So I've written it in symbols, but here's the picture. So so if I want to work out what is the Stokes factor associated to this red ray here, then I take two non-Stokes rays, which are perturbations of it, and then I have a unique solution there, and I have a unique solution there, and then they're both solutions to the same differential equation, so they differ by a constant, and that's my Stokes factor. How are we doing? Okay. So basically, given a differential equation of that form, we get a diagram exactly like the one we've been considering. We get a bunch of rays in the complex number, the Stokes rays, and associated to each of the rays, we get an element of the group. And you can easily see that this isn't any arbitrary element of the group. It has to lie in this part of the Lie algebra, which is namely the exponential of the part of the Lie algebra which is mapped by U onto that ray. And if you sort of compare that with the formula for the DT wall crossing automorphisms I had before, then you'll see it's kind of the same form. Anyway, so that's the kind of analogy we want to pursue. The idea is that that ray diagram with the DT orthomorphisms should be thought of as Stokes data, but the group is not G because the elements we're considering associated to these rays are not matrices, they're orthomorphisms of the torus. So every time we see GLN, we need to replace it by orthomorphisms of the torus. That's somehow the idea. Okay, so what about this Riemann-Hilbert problem? Suppose I gave you the Stokes data and I asked you what the differential equation was. How would you get it? Well, the idea would be you would first, it's not really worth it. You would first get these canonical solutions, y epsilon, and then you could just differentiate them and that would give you back the connection. It would give you back the matrix V, which is really what we're after. So how do you do that? So this is going to be this Riemann-Hilbert problem. So it sort of tells you itself. So for each non-Stokes ray, you need to find some function to G. That's going to be your fundamental solution. It should have these asymptotics as epsilon goes to 0 because the fundamental solutions did have that property. It should not grow too fast at infinity. That's because your differential equation had a regular singularity at infinity. So solutions to differential equations near regular singularities just have polynomial growth, so kind of moderate growth. And then if you compare the solutions on two of the rays, of course they should be related by the Stokes data. Okay, so if you compare the solution on one side of a ray to the other side of the ray, it should just differ by the Stokes factor. Since later we're going to want to think about the possibility where there's infinitely many rays, a nicer way of saying that is that if you have a convex sector, then the with boundary rays R plus and minus, then they should differ by this product of Stokes factors. Okay, so that's how you try and get the solution back. And you can, yeah, I mean, existence and uniqueness of these problems is kind of an interesting thing, and I'm not going to go into it just now. But so for now, you should just consider this as an analogy. Okay. So that's the motivation to state the following thing, and this is yeah. Why don't I just put it all down and we'll just stare at it in horror for a few moments. So the first thing to say is that this is going to give, in a very simple example, this will reproduce the problem I started with in the introduction. So that was an example of one of these DT Riemann-Hilbert problems. Yes, so where does it come from? So to define one of these problems, I basically want a stability condition. Okay, but I don't actually need all the categorical stuff. What I really need is the charge lattice with the form on it, the central charge, and I need to know what these DT invariants are. So I just want some numbers, the DT invariants. It doesn't really matter for the formulation of this problem whether they're actually DT invariants or just some random numbers you just thought of. And I also need to choose a point of the torus. And the reason I need to choose this point of the torus is I don't want to formulate the problem as something taking values in the group of automorphisms of the torus. That's an infinite dimensional group and it's kind of scary. So instead of that, I fix this point and I evaluate all automorphisms on that point. Okay, so then instead of going into the group of automorphisms of the torus, I just go into the torus. Okay, and then I just have the same sorts of things that you saw before. Okay, so there's some asymptotics at 0 and infinity, and the jumps are controlled by these Stokes data things that we had before. So these are these automorphisms that crop up in the wall crossing formula. Yes.
Wouldn't the automorphisms be ill-defined if the omegas were not integers?
Um,
They're in the exponential, you'd have fractional powers.
Yeah, no, I mean, absolutely what you're saying is correct. I'm just trying to think why I'm not worried about that. I tend to define them using the first formula, actually, because that's how I get them. I mean, the DT invariants are given to us in that kind of rational form, usually. And so I use, remember, I had this time one Hamiltonian flow of the other guy.
But the usual product formula might then not.
Then that might not hold. But I mean, if you like, I mean, assume that they're integers. Yeah, absolutely. I mean, I have not considered any cases where they're not integers, certainly.
Okay.
I think what you're saying is completely correct. Yeah. 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 Okay. So yeah, so this is a kind of a scary thing, obviously. We're looking at maps from half planes into the torus with asymptotics at 0 and infinity and certain controlling jumps. The sort of surprising thing is you can do anything with this, I suppose. So let me just say how this works with the example from the introduction. So in that case, you should consider just a rank 2 lattice with this form. And I guess I'm using physicist notation where this will be the electric and magnetic charge. But it's just a rank 2 lattice. And I set the central charge of this guy to be Z, and actually I'm going to take the central charge of the other thing to be 0. I could actually put anything here, it doesn't really make much difference. And the only non-zero BPS invariants are the electric guys for 1. And so here we already see that there are only 2 Stokes rays corresponding to Z and minus Z. And so we're going to be looking for solutions on half planes spanned by non-Stokes rays. But you see the jumps only happen across these rays. So if I have an analytic function on this half plane for each of these blue rays, then when I glue them all together, I'll end up with an analytic function on the whole plane minus this slit. If you sort of imagine rotating this picture without letting the blue arrow cross the red arrow, you would fill up the whole of the plane minus this slit. And that was what appeared in that problem before. So I'm going to take this constant term to be trivial. And so the jumping is controlled by the dt invariance, right? So, and in the wall crossing formula, there's some kind of pairing happens. So because the dt invariance is only non-zero for the electric charge, that means that the electric character doesn't jump, whereas the magnetic character jumps by the electric guy in this way. But since the electric guy doesn't jump, it will just be equal to it. The solution will just be equal to its asymptotics. So the solution to the Riemann-Hilbert problem, yeah, it's a map into the torus, but then I can look at the characters, right? So I get a map into C star for each charge. And so I claim that the guy for the electric charge is just going to be equal to its asymptotics. That solved the problem because it doesn't need to jump. And so then if you think about how the other guy is going to jump, like this, then you exactly arrive at the Riemann-Hilbert problem I started with. Okay, so that was a special example of what I'm talking about here. Yeah, and then you get the gamma function and blah blah. Okay, so let me. I'm just going to give you another example. I'm not going to go through any of the details because they're, that would take ages. But let's indeed consider the resolved conifold and the derived category of coherent sheaves. I should say compactly supported. And I take some stability condition. I mean, we know about stability conditions on this thing. And let's take the central charges to be, this is the kind of D2 brane should be V and the D0 brane should be W. Here's the ray diagram at this particular central charge, where I guess this is the point V and this is the point W. And okay, so I'm missing a whole load of steps here. The Riemann-Hilbert problem has a unique solution, and I can define that tau function just in the same way. And this is what I get. And maybe I should give you the full thing. I get this function, which we could return to. And when we expand epsilon goes to 0, we get a few sporadic terms, which I've missed out, and then which are a bit unpleasant and mysterious maybe, but I mean, they're no big deal. And then in higher genus, we just get the Gromov-Witten generating function of the resolved conifold in this parameter, epsilon over W. So you can try and call this a non-perturbative partition function in that it's some particular analytic function who has whose asymptotic expansion matches this this generating series. And actually, this is a pretty pleasant function. It's called the Barnes triple sine function, except I've used repeated arguments. So this epsilon has entered twice here. And I suppose if you're into refined stories, this should actually be epsilon 1 and epsilon 2, and then it really would be the triple sine function. And this is this is sort of this is the pre-potential that's being subtracted for some reason. That always seems to happen. Anyway, so this is not a precise science at this point at all, but it's remarkable that there is a unique solution to the Riemann-Hilbert problem in this case, and it gives you a nice answer for a potential non-perturbative partition function in this case. Okay.
Sorry, can this be recovered from the topological vertex, or is that not going to work?
I think not, because I mean, I'm not really the person to answer this, but I think not.
Or is the topological vertex just going to give you the asymptotic expansion?
I think it's just going to give you the asymptotic expansion. Yeah, yeah.
I think that, yeah.
I mean, one of the points is that if you, yeah, okay, no, let me not go into. I don't know enough about that. But there's a very nice paper by Murad Alim and Jörg Teschner and collaborators, Ivan Tully, talking about exactly this example, and Borel summing the topological string partition function. Yeah, so I mean, it involves very similar objects, but by people who really know string theory. So that might be a good place to look for.
Okay, that's a better answer. Can you get that by Borel summing the a better question? Could you get that by Borel summing the asymptotic expansion that you wrote down at the bottom?
Correct. Yes, you can, and that's what they discovered. So that's going in the opposite direction. That's starting with this guy, Borel summing it, and you do indeed end up with this. Yeah. Yeah. And I guess for many physicists, that would be a more appetizing thing to do, right? Start with this thing, yeah, and Borel sum. I mean, whether that's always going to work, I'm not sure. But for me, somehow, I mean, this was just a kind of unexpected output, which is nice for trying to grab people's attention. I mean, for me, really, the story is that you have these DT invariants. They absolutely behave like Stokes data. So you're sort of forced to try to understand what is the differential equation whose Stokes data is these things. I mean, that's really my motivation. And the fact that, you know, and to get at that differential equation, you have to solve this Riemann-Hilbert problem. And the fact that you get these very interesting answers out is some sort of indication you're on the right lines, but that wasn't really the main goal. Yeah. Okay, so let me talk about this, some of the outputs. So as I was saying, it's not really for non-perturbative partition functions that we came into this game. So I want to discuss, so for some people who know about these things, that connection I had earlier in the GLN case, that's actually a connection that you get at each point of a semi-simple Frobenius manifold. So if anyone's studied the papers of Boris Dubrovin on this topic, he really goes into detail on this. And it's almost an equivalent formulation of a Frobenius manifold, a semi-simple Frobenius manifold anyway, is some isomonodromic family of connections of that form that I just discussed. And so what I'm now saying is, what is the analog of a Frobenius manifold if I change the group GLN to this group of automorphisms of the torus? What is the analogous geometric structure? Because that's actually what we're going to be getting on the space of stability conditions. So I'm going to tell you what that structure is now. So I take some complex manifold with, and I write X for the total space of its tangent bundle. And then there's a sort of trivial short exact sequence, which I've written in funny language. So I'm just considering the derivative of the map pi. Okay, so it goes from the tangent bundle of X to the tangent bundle of M. But so that all the bundles live on the same space, I should pull this guy back. Okay, so but this is just the derivative of pi. It's a bit confusing because X is the tangent bundle. Anyway, there you go. So I think of these as the vector, you know, sections here are vector fields on X, and these are the vertical, okay, sorry, these are the tangent vectors to X, and these are the vertical tangent directions for this map. Okay, there's a slightly confusing but trivial point, which is that the vertical tangent directions for this map are the same as the tangent space to M, okay, just because it is the tangent bundle. So, you know, if you have a vertical tangent direction here, the fibers of this map are the tangent spaces of M, so you can identify it with the tangent space to M. Okay, so there's a canonical isomorphism here. And now we want to talk about nonlinear connections or Ehresmann connections. So an Ehresmann connection is a splitting of this sequence. It's a way, you know, you always have vertical tangent directions. An Ehresmann connection gives you a notion of horizontal tangent directions. Okay, and the way you can think about that is it's just a splitting of this sequence. So it's a way of lifting tangent vectors from downstairs to tangent vectors upstairs. You could say this about any map pi, but we just happen to be applying it to the tangent. Okay, so it's a splitting like this. And so here's the definition of a pre-Joyce structure. So sorry for the horrible terminology. So on a complex manifold, what is it? You have a holomorphic symplectic form, and you have some nonlinear connection. And then what you need, you see, once you have one way of lifting tangent vectors, you can modify it by adding a bit of vertical stuff. Okay, I'm just adding epsilon inverse times this vertical stuff. And what I want is that each of these connections is flat and symplectic. So if you think the fibers of this map are naturally symplectic vector spaces because we have a symplectic form on the tangent bundle. So yeah, so that's the condition. And what I want to say is that this is basically some kind of analog, nonlinear analog of a Frobenius structure. A Frobenius structure, people talk about multiplications on the tangent bundle, but really the important thing is that you have a one parameter family of flat torsion-free connections on the tangent bundle. Of course, in that setting, they're linear connections. And in this setting, I'm talking about nonlinear connections. But nonetheless, the key thing is that you have this one parameter family of connections. So that's the definition of a pre-joist structure. And just as with the, in a Frobenius manifold, you have all these kind of extra whistles and bells. You have kind of an Euler vector field, you have an identity vector field, all this stuff. And similarly, there is a notion of a joist structure, which I'm not going to go into for lack of time, which has just some extra data. And so what did this have to do with this Riemann-Hilbert problem I was talking about before? So if you remember, this depended on some stability. So M is going to be the space of stability condition. The Riemann-Hilbert problem depended on a stability condition and also this constant term, this element of the torus. Now, if you remember, the tangent space to the space of stability conditions was just this, because it's just controlled by the central charge. So the tangent space is just this, and this was this torus. So you can really think about this data. I mean, if you just pass to the cover, this is really an element of the tangent space. So you can think of solutions of the Riemann-Hilbert problem as depending on a point of the tangent space and mapping you into the torus. Okay, so yeah. And then if you think about the dimensions here, if this has n dimensions, the dimension of your charge lattice, this has dimension 2n because you know, the central charge can vary in n ways and this constant term can vary in n ways. So this is 2n dimensional, this is n dimensional. You just take the kernel of that, of the derivative of that map, that's going to give you this pencil of flat connections. So that's somehow how we get them. We look at so basically what is this machine saying? It's saying that if I deform the central charge, how do I deform the constant term so that the solution to the Riemann-Hilbert problem is constant, is unchanged? Yeah. And then, yeah, I just wanted to, what I was saying a bit before, I mean, there is the joist structure has some extra compatibilities. So the space of stability conditions already has some extra structure, namely, it has an integral affine structure, it's got a C star action on it, and there is some compatibilities with those things that I won't go into the details. Okay, but that's, okay, so obviously solutions to this Riemann-Hilbert problem, that's a pretty difficult thing, but we can at least go out looking for these joist structures because that's just, you know, it's perfectly nice notion. It's a bit of complex analysis. And I'll skip that comment. Okay, and so I'm very nearly out of time. So what I just want to say is that there is a class of examples where we can find these joist structures. So at warp speed, let me tell you what some of you already know, that there are some examples of categories, CY3 categories, very nice ones. I like to call them categories of class SA1, where we can completely describe the space of stability conditions, and it turns out to be a space parameterizing quadratic differentials. So more precisely, pairs consisting of a compact Riemann surface of genus G and a quadratic differential. And usually we think about the case with poles because that's easier actually for many reasons. But this result has been extended to the case without poles by Fabian Heiden. And so we can look for a joist structure on this space of quadratic differentials. And what I just want to say is that we can do this. So I've done the holomorphic case and it's on the archive. And my student Menelaos Zikidis is doing the case where you would consider about quadratic differentials with poles, where now it's not easier, it's definitely harder this way around. And so I just finished here. So I I just want to try and advertise this structure because I think it's a rather beautiful thing. So you have this nice algebraic variety parameterizing Riemann surfaces with quadratic differentials. And you can build this one parameter family of nonlinear connections on its tangent bundle. And the way you do it is you use various moduli spaces of connections and Higgs fields, very much as is kind of, done. I mean, it's very reminiscent of work you see relating to the Hitchin system, for example. But I just want to emphasize that this thing is much simpler than the Hitchin system. Of course, it's not as rich and amazing as the Hitchin system, but it has some advantages that it's computable. In particular, it's algebraic. So all these connections are algebraic. And in simple cases, so this is my favorite case, genus 0 and a single pole of order 7, the corresponding category is basically given by the A2 quiver. So as a category, it's a ridiculously simple thing, but nonetheless, this joist structure is extremely rich and non-trivial, but you can write it down with explicit formulae, and it relates to things in integrable systems. So it's very closely related to Painlevé 1. Okay, so I just wanted to advertise these things. They're on the archive. If you're interested in Higgs bundles and things like that, go take a look. I think they're fun. But I should stop there, and thank you very much.
Thank you, Tom, for a great talk. Appreciate it. And we have plenty of time for questions.
Tom, I have a question. Can you prove in this abstract setting that if you have an exponential bound on the T invariance, which you wrote earlier, then the solution to the Riemann-Hilbert problem, or rather any holomorphic section of the bundle which you can glue from that are resurgent?
I certainly can't, because I don't know what resurgent means, I'm afraid. I mean, I sort of do.
Barrel summable in what was mentioned previously. It's Barrel summable and infinitely analytical. So you take formal series, which is expansion at 0.
Mm-hmm.
I forgot what. Okay.
Yeah,
so
sure.
then it's in general it's divergent. Yeah. But the bundle which you glue using these Stokes automorphisms with exponential bounds on the T invariance, it's holomorphic. So then each sector you have a section which you can expand its divergent series, but you can take the Barrel transformation and try to extend it infinitely. So
Yeah,
then the question is whether it's possible or not, especially when you have like dense set for the central charge values when the image of the charge lattice is like everywhere dense, for example. Yeah, so then that's the question whether this Barrel summation gives you the convergent series.
Near the origin. Oh, and then it should be analytically continuable, right? I mean, yeah, the simple answer is no, I don't know how to do that. I mean, I should mention that for the rest of the audience, so Maxime and Jan have this very nice sort of approach and result, which says that if you have this sub-exponential growth, and actually they assume something a little weaker, but anyway, if you have this sub-exponential growth, then you can kind of build a complex manifold so that solutions to my Riemann-Hilbert problem are kind of you can sort of build a bundle over the disk so that solutions to my Riemann-Hilbert problem would just be sections of this bundle, except that you have to drop one of my conditions. So I don't know whether we can get back to that. So yeah, it makes sense to just show this. Yeah, so if I forget about the behavior as epsilon goes to infinity, which they don't consider, if you just consider this and these problems, you can build a bundle over the epsilon disk such that sections of this bundle exactly give you solutions to this Riemann-Hilbert problem. But then you're saying we could think about expanding those, and asking where, I mean, of course, I don't know the answer to your problem. Do you?
No, I mean, I'm asking because I don't know. It's a conjecture.
Yeah.
And since our kind of abstract setup is slightly different, I'm wondering whether you can prove this kind of result kind of in your framework. Yeah.
No, I mean, what I've been wanting to try to do is take what you did over epsilon equals 0, actually, but in a slightly different, in this kind of twistor space formalism rather than at each point on the stability space. But then try and glue in behavior at epsilon is infinity so that you really get something compact, and then you might expect that there aren't too many sections, right? Then the space of sections is a tightly controlled thing. It's just going to be a finite dimensional space of sections. But the question is, can this be done in any generality?
Yeah, and I forgot, everywhere dense set of periods, is it good, okay with you, or you want at least have at least some sectors free of dense?
Yeah, no, I haven't got it. I mean, together with Helga Rudder, we're thinking about the case of ADE quivers. So then there's only finitely many chambers. So
I'm rather thinking about holomorphic Chern-Simons. And when you have periods of the three form on your Calabi-Yau, and it can be everywhere dense.
Yeah, I mean, I kind of feel I always like to just understand the simple examples. My hope is that these things about everywhere dense and stuff will, once you understand the right picture, then it will be fine. But that's what I hope. But no, indeed. I'm behind you on this, Jan. So no, I can't answer your question. Sorry.
All right, thank you.
Other questions?
I have a question.
Go ahead, Greg.
Yeah. What's the physical interpretation of a joist structure?
Yeah, that's a good one. I mean, I mean, it should have something to do with the conformal limit, right? Do you allow me to say that? I mean,
what? Just because there's a what? What was the deformation? The deformation was by epsilon v. So you're saying it's epsilon v and not epsilon v plus 1 over epsilon v prime or something?
Well, I just wanted to say that you had a Riemann-Hilbert
family. Yeah, the family of flat symplectic connections. Maybe you could write that. Go to that slide. Yeah.
Yeah. So yeah, exactly. So it's like this, right? So you would have considered one with zeta inverse and zeta. So it would have a pole at 0 and infinity, whereas I've got something simpler. And it is. I mean, as I was trying to use the propaganda, I mean, it is more computable. The structures I'm getting out, the solutions to this problem are kind of more computable than trying to compute the Hitchin metric, which is what you were essentially doing, right?
Yeah, I get that, but I'm just wondering whether this has a physics name.
Well, it must have something to do with the conformal limit, right? Because if you take your thing and you know this.
I agree. But okay, so you can take the conformal limit, but I mean, what is this thing? And structure something that I should know about in the physical system. That's what I'm wondering.
I mean, I don't know whether. I mean, Boris and Sergey may be in the audience. They may be able to help me at this point.
I thought them, so maybe they could answer.
But I mean, the way I think about this is it's something where you start with a hyperkähler manifold, a real hyperkähler manifold with a C star action, and you somehow kind of blow up near the origin of the twistor space using the C star action. And what you end up with is this kind of structure. But I haven't worked out how to express that rigorously. I mean, that's just a kind of idea in my head.
I mean, solutions to the Hitchin system give you, well, I don't know, they give you things like superpotentials for surface defects and stuff like that. So I'm just wondering if there's some analog of that for
Maybe I can add about this. We have a result which relates a solution. So in this joy structure, one gets some sort of Klebanski equations, and there is a potential, there is a function which solves this equation. And so this Klebanski function, it's very closely related to, maybe you know, it, we call it contact potential. Actually, in physics, it's very close to the dilator.
Index.
Yeah, also, yes, exactly. So one can think that about this quantity, its conformal limit, and in the conformal limit, the instanton part of it, it essentially coincides with this Klebanski function.
Okay, thank you.
And I should just add that the Plebanski function is just what you get when you write this connection down in terms of, yeah, I mean, in coordinates. So indeed, the Plebanski function is exactly describes this structure. Yeah. Thanks. Thanks, Sergey.
Well, what I'm getting from that, and I mean, something which I would find a little more satisfying is relating it to some kind of index. So Sergey mentioned a contact potential, and there is some connection between that and an index of the four-dimensional theory on R3 times time.
Are there other questions? Well, quick question. So you were talking about the epsilon 1, epsilon 2 refinement
Yes.
in the case. Is that can you say anything more in a more general context? With regard to Riemann-Hilbert problems?
Yes. Well, I probably can't give the correct references, but I can give the idea, which is just that you can form a refined version of these Riemann-Hilbert problems wherever it was, at least in principle, where because these wall-crossing automorphisms have canonical quantizations or refinements, where instead of automorphisms of the torus, you talk about automorphisms of the quantum torus. You know, in many ways, that's the most natural thing in DT theory. So there's some extremely natural place where you replace these with automorphisms of the quantum torus and just formulate the whole problem.
Right.
And then if you do the same steps, you should expect to get the fully refined thing. But
thank you.
But it's pretty tricky actually, because here we had to go a bit analytic and start talking about open subsets of the torus, analytic open subsets of the torus. It's not so easy to do that once you do quantizing, once you're talking about a non-commutative thing like the quantum torus. And so I guess possibly at that point, really what you should do is take some representation of the quantum torus in Hilbert space or something and really do something like that. So I think it's not so easy to do calculations, but they have been done, particularly in the conifold case. These calculations are in the literature.
Yeah, thank you. Are there other questions? Okay, well, if not, then let's thank Tom again.
Thanks, Sheldon. Thank you.
And the next talk in our series will be Miranda Chang talking on March 11th. Hope to see you then.
Thanks, everyone. Have a good day.